Okay, first of all, hello, future people.
Hello,
I like
future
saying
people.
that. Secondly, we're doing something slightly different. If this turns out well, I'm the one reading today instead of Lemos. So, and also there's my face. So there we go. Um, so yeah, today we're doing chapters 15 and 16. Yoneda Lemma. Um, what to say about the Yoneda Lemma? Okay, so most constructions in category theory are generalizations of results from more specific areas of mathematics, which is something that we've seen so far, right?
Yeah.
Um, they have been known under different names: Cartesian product in set theory, meet in order theory, conjunction in logic. We know those. They are specific examples of the categorical products. The Oneda lemma stands out in this respect as a sweeping statement about categories in general, with little or no precedent in other branches of mathematics. Yeah, the Oneda lemma is a bit of a wild one, as we will see. Um, Cayley's theorem in group theories, apparently its closest analog. I don't really know group theory that much, so I don't know Cayley's theorem in particular, but well,
Neither
it
do I.
says here. Anyways, the setting for the Oneda lemma is an arbitrary category C together with a functor f from C to set. This part here is important. We've seen in the previous section that some set-valued functors are representable, that is, isomorphic to a home functor. And the Yoneda lemma tells us that all set-valued functors can be obtained from home functors through natural transformations. And it
Okay, stop.
explicitly... Okay.
I want us to go back a little bit and try to remind everybody of what the heck is a home functor. So a home functor, as I was talking to Marinho before we started recording, a home functor is the functor that goes between pairs and sets. Because you're grabbing two elements, so of any category, let's say the elements are called A and B, and you're grabbing that pair and mapping that to the category of sets, specifically the home set
Yeah,
between A and B.
it's actually a pair of categories in particular for the home functor because it's a functor, right? It's between categories. Um,
Yes, yes.
um, yeah, and natural transformations we saw that fairly recently. I don't think we need to elaborate too much on those. They're pretty neat. They're
Yeah,
pretty
natural
natural.
transformations are how you bridge functors. That's
Exactly.
that's it.
When I talked about natural transformations, I mentioned that the naturality condition can be quite restrictive, which will play an important role here. When you define a component of a natural transformation at one object, naturality may be strong enough to transport this component to another object that is connected to it through a morphism. The more arrows between objects in the source and target categories there are, the more constraints you have for transporting the components of the natural transformations. And set happens to be a very error-rich category. Yeah, pretty much everything is connected to everything in set. No, we saw that a while back.
Yeah, pretty much everything is connected. And again, this definition that Marinho just read, we're gonna see a little bit more with the drawings below.
Yes. Um, let's see. The Yoneda lemma tells us that a natural transformation between a home functor and any other functor f, is completely determined by specifying the value of its single component at just one point, which is kind of crazy.
Yeah, but what does it mean to say 1 point? What is a point in this case?
A point would be a specific input or a specific output. Well, input output in quotation marks, right? Because we're dealing with category theory, not function theory, right?
Yeah.
But yeah, by point, it means a specific object that's either a valid source or target for the functor.
Mm. Okay. So what you're saying is the natural transformation. So I have a functor here and a functor here, and a natural transformation between those. We can fully determine the natural transformation between them by specifying only one of them.
Yeah, the rest of the natural transformation follows from naturality conditions. It's like, it's really nuts.
Yeah, but there is a catch. One of them needs to be a home functor.
Indeed, one of them, the source needs to be a home functor specifically.
Okay.
So let's review the naturality condition between the two functors involved in the Yoneda lemma. First functor is the home functor. It maps any object x in C to the set of morphisms C from A to X for a fixed object in C. So we're fixing the source of the morphism.
Yeah, but A is an object of the category of C, which is a home set, right?
The first functor is the home functor. It maps any object
X in
X
C.
in C
Yeah.
to the set of morphisms. Yeah, it maps an object to
A
a
home
home
set,
set.
in which
Exactly.
the first member of the bridge of the home set is fixed.
Yes, we fix it to some arbitrary object
Yeah.
that can be a source.
Yeah.
We've also seen that it maps any morphisms F from X to Y to CAF with no risk of confusion. I'm gonna keep I'm gonna keep hitting that key. This is why, just why.
But let's remind ourselves, because I remember that session of like no risk of confusion, and then I was confused. So let's try to remember what the heck does it mean to say CAF in there?
It basically means that this is actually something that looks more like. I think there's an example lower here somewhere. We'll get to that, but basically this is a morphism. So actually, this entire thing is a morphism, where the left-hand side is CAX and the right-hand side is CAY, because those are the input and output of types of F.
Okay, you said CAX and CAY.
Yeah.
Oh, I remember. I think I remember. I think I remember that. Yeah. It's all the possible combinations of the input of F with the fixed value of A, and all the possible combinations of Y, which is the output of F, with all the possible combinations of A.
Yeah.
Well, A is fixed, so there is no combination. Only there's only one A. Anyway, move on.
The second functor is an arbitrary set-valued functor F in capitals.
What does it mean to say set-valued functor?
That means it's a functor where the target category is set.
Yeah. Okay, let's move on.
All right, let's call the natural transformation between these two functors alpha, because apparently they like using alpha for natural transformations for some reason. Because we are operating in sets, the components of the natural transformation, like alpha at x or alpha at y, are just regular functions between sets. So, yeah, because a natural transformation is basically these two arrows here, right? The ones going downwards. But the target object is inside of set, so those are set functions.
Yeah, so we are going from the set C to the F, and F we know is a set valued is bringing us to a set anyway, because F is a set valued functor. So F of X
Yeah.
is a set, C is a set. That means that the natural transformation is a function on sets.
And because these are just functions, we can look at their values at specific points. But what's a point in the set C of A and X? Here's the key observation. Every point in this set is also a morphism H from A to X.
Wait a moment. Every point in the set CAX is also a morphism H from A to X.
Yeah, because this is a home set, right?
This is a home set.
So by definition, everything here is a morphism that takes an A and returns an X, to borrow some programming language.
Oh, okay. Every point in the home set. Okay, I forgot about that. Okay, let's continue.
So the naturality square for alpha, which is this, represented.
You can derive that from the drawing. right? We are basically saying that if you go CAF, then alpha at y is the same as picking the alpha at x and moving FF.
Yeah, and this thing becomes pointwise when acting on age, this. So F is age, this is an F map basically, and this is, well, this.
Wait, I don't know if I follow. How did we go from the previous naturality square to that? How did we introduce H exactly?
Uh, well, this is alpha after this thing and f of f after this thing. Those are, I'm not, I don't want to call them functions because they are not, but
Well,
let's think of them
it's
as
yeah,
functions.
but it seems that they are both a natural transformation and a function.
Basically, you're giving age as an argument to those things. See, a of x of age, and then you pass the result to this, which is,
uh,
it's the same as just this thing here. If you put parentheses around it and give it, apply it to age, and you evaluate a little bit,
oh,
you get this.
oh, I see, I see. Okay, but on the right, the notation is a little weird. I was expecting more parentheses. But that's okay. No, that's okay. I see, I see. We can continue.
You might recall from the previous section that the action of the home functor C from A on a morphism F was defined as precomposition. So this,
Mm-hmm.
which leads to this thing here,
Mm-hmm.
and just how strong this condition is can be seen by specializing to the case of x equal A. So like, okay, we're specializing the output, which is a variable, to
To
be equal
identity.
to A, which is
Well,
the fixed input.
yeah.
So in that case, H becomes a morphism from A
A
to
to
A.
A. Mm-hmm.
We know, someone joined.
Nathan.
Hello, Nathan. I cannot see the chat, by the way.
Yeah, we're gonna work on that next time.
We know that there is at least one such morphism, which is A, H equals identity at A. Let's plug it in.
Mm-hmm.
So there we go. Notice what has just happened. The left-hand side is the action of alpha at y on an arbitrary element f of C from A to y. And it is totally determined by the single value of alpha at A at identity of A.
Okay, wait a moment. So the left-hand side is the action of alpha at y on an arbitrary element, CAY,
Yes, which is called f here.
and it is totally determined by the single value of alpha at A at identity A.
Yeah, because like algebraically, uh, if you could somehow isolate this f and move them both to like, I guess that's not really a thing, right? When you're not, I mean, it kind of is, but not for like execution. The point is, you have this f here, which is the
Uh-huh.
parameter for this natural transformation, and that's the only variable on the left-hand side.
The F.
Yeah, which is the input variable, so it needs to be there.
Okay.
This is basically a function definition in Haskell, right?
Yeah.
And it is totally determined by the single value at this, like identity array. We can pick any such value and it will generate a natural transformation. Since the values of alpha at A are in the set f of A, any point in the f of A will define some alpha. Conversely, given any natural transformation alpha from C of A blank to F,
Mhm. Mhm.
we can evaluate it at identity at A to get a point in FA. And we have just proven the Yoneda lemma, apparently.
There is a one-to-one correspondence between natural transformations from that to F and elements of F of A. Okay, let's try to read that a little bit more again. There is a one-to-one correspondence between natural transformations
Yeah. Mm,
Hmm. Okay, I don't know if I fully got it though. I don't know if I fully got it. Oh. Okay, can we scroll up? Yeah, a little bit. So in that equality there, and when we're swapping, oh yeah, the alpha at y f equals that thing.
this one, right?
You said that the only thing that is varying there is the f, the non-capital F, right?
Yeah. On the left-hand side, at least.
On the left-hand side. And the reason is, why is the alpha at y not a variable in this case?
This is what we're trying to define, right?
We're trying to define alpha at y.
Yes, if we're trying to define this, and this is the only variable, but that's fine because it's a natural transformation. It's supposed to take, well, a parameter, right?
Mm-hmm.
If this is the only variable on this side, that means, well, we have a full definition here.
Okay, so the alpha at y is a natural transformation. It expects an argument. That's okay.
Actually, it's not even a full natural transformation. It's a component of a natural transformation at a single point, right?
Yes, I also remember that. Then we have on the right hand side f of f. Well, we are lifting f. That's it. And what we had is alpha at a and identity of a.
Yeah.
Mm. It is totally determined by the single value of alpha at a. We can pick any such value and it will generate a natural transformation. Since the values of alpha a are in the set f of a, any point in f of a will define some alpha.
Yep.
Okay, let's continue. I'm still digesting this. I don't know if I get it.
All right. So in other words, this, which is basically this, but written more compactly, it's saying here that a natural transformation from this thing to this is isomorphic to f of a. Or if you use this notation, which they are introducing for the functor category between C and sets,
I have a question.
yes,
C, A, and then dash, that's a home set, right?
this is a home functor actually with the a fixed.
Oh, oh, this is a home functor.
Yeah, this net here is the category of natural
Yeah,
transformations,
no,
net
between
of those
this and this.
things.
So the two
Yeah,
things need to be functors. So you're right. C, A dash is a functor, F is a functor, F is a set valued functor, and C, A dash is a home functor. Is a home one.
yeah,
Okay, now I see how insane this is. Because we are basically saying that the home functor in which goes from a pair to a set, you can fix only one of the things and the other thing can vary, and have a functor that the destination is set valued, and you don't need to care about the other guy that is varying. You only need the A.
yeah.
Now I see.
Isomorphism, very strong restriction.
Yeah, I see, I see. We can continue.
So yeah, if we use this notation here for the functor category between C and sets, the set of natural transformations is just the home set in that category, and we can write it like this.
Okay, let's go up a little bit. The set of natural transformations is just a home set in that category. I don't know if I got it. I got what that means. If we use this notation for the functor category between C and set, the set of natural transformations is just a home set in that category. It's a home
Yep.
set between what?
It's a home set
Between two functors.
between two functors, yes.
Okay, I see. I see. Let's go on.
I'll explain later how this correspondence is in fact a natural isomorphism. Now let's try to get some intuition about this result. The most amazing thing is that the whole natural transformation crystallizes from just one nucleation site. And this is a very inspired bit of metaphor here,
Yeah.
crystallization. The value we assign to it adds identity of A. It spreads from that point following the naturality condition. It floods the image of C in set. So let's first consider what the image of C is under C from A to, the home functor.
Okay, so C in that case is a category.
Is a category, yes.
And the other C with the parentheses is a functor.
Is the home functor.
It says specifically the home functor, yes.
Specifically the home functor with the A fixed, fixed objects. Let's start with the image of A itself. Under the home functor, A is mapped to the set C from A to A. And under the functor F, on the other hand, it is mapped to the set F of A. The component of the natural transformation is some function from this to this. So let's focus on just one point.
Wait. Go up a little bit.
Going up?
Yeah, this session is going to be long because we are basically reading the entire chapter because the entire chapter is dense. That's basically
it's packed full of information. Very nice.
So start with the image of A itself. Under the home functor, which I understand what it is, A is mapped to this set.
Yeah.
A is mapped to this set. Oh, we are fixing the varying thing to A itself.
Yes.
Under the functor F, on the other hand, it is mapped to the set FA.
Well, yes.
Yes, the component of the natural summation alpha at A is some function from C AA to FA.
Yes.
Okay, so that C is a functor. No, that actually is not a functor anymore, right? CAA is a home set.
It is a home set. Yeah, if you look at the picture here.
Yeah.
That
it is
help.
A home set in this case because we are fixing the destination, and the F of A is also a set.
Yes, because it's a set-valued functor, so by definition, this thing here.
Okay, so we are going from one set to the other set.
Yes, we are.
Oh, I see.
Yeah, and this is the component alpha of the natural transformation. So let's focus on just one point in the set, the point corresponding to the morphism identity at A, which is this one, right?
Mm-hmm.
To emphasize that it's just a point in a set, let's call it P, which is right here. And then the component alpha at A should map P to some point Q in F of A. And then I'll show you that any choice of Q leads to a unique natural transformation.
So, should map P to some point Q in F of A.
Yes.
I'll show that any choice of Q leads to a unique natural transformation. Okay, so you're choosing Q. You have to pick P, and you're going to have alpha at A immediately.
Yes.
I see.
The first claim is that the choice of one point Q uniquely determines the rest of the function alpha at A. Indeed, let's pick any other point P prime in C from A to A, corresponding to some morphism G from A to A. And here's where the magic of the Yoneda lemma happens. G can be viewed as a point P prime in the set of this one. At the same time, it selects two functions between sets. Indeed, under the home functor, the morphism G is mapped to a function C from A to G.
With no confusion in there. Okay.
And under F, it's mapped to F of G, which is the F mapping in this case, right?
Okay, wait a moment. G can be viewed as a point P prime in the set P prime.
Yes, because this thing here is the home set from A to A,
no, that
right?
makes sense. No, that makes sense.
And G is a morphism from A to A, so it must exist here.
Okay, so we are basically, indeed, under the home functor, the morphism G is mapped to a function. Wait a moment, I don't know if I got that part. Under the home functor, The
Yes.
morphism G is mapped to a function
Yes.
CAG.
Specifically this function here, this arrow right here.
Yes, I can see that. But why?
Because because basically when you do this thing here, when you apply it through, well, when you look at it from C from H way, because G goes from H way, it must exist here.
Yes,
But you
I
can just
understand.
apply, but you could just as well apply the home functor and lift G into it like this. See the C from A to G here off to the side.
Ah, ah. Okay, but that's really confusing. Why is the arrow? Why is this identity? Why is it saying it as like the arrow that points to itself? The arrow that.
It's not identity necessarily. It's one moment.
No, no problem.
Yeah, it's not identity necessarily. It's just well, specifically it's not identity because identity is right here. But this is just an arbitrary morphism from H way. It doesn't have to be identity necessarily.
Yeah, yeah,
Probably
but
isn't.
why is it pointing to itself on the home functor thing?
Because if you lift it, right?
Yeah.
If you lift it, then well, it will lift both the input and the output variables, right? And they will both just become C from H way.
Ah. Okay, I see, I see, I see. That makes total sense. That makes total sense. Now let's consider the action CAG on our original P. On our original P, which, as you remember, corresponds to identity of A.
Yep.
It is determined as P-composition, this, which is equal to G. Because that's identity.
Yeah, that's identity.
Wait a moment, I need to remember, what does it mean to say CAG on our original P? On our original P.
Because there's P, which is the
I remember that.
identity, yeah, the identity arrow viewed as a point in this set, in this home
Yes.
set.
Yes.
But because this morphism here takes something from the set to back to the set itself, it can take P as an argument, so to speak.
G.
This lifted G actually can
Oh,
take
you
P.
can pick the lifted G. Okay, that's
Yes.
important. I was kind of lost on there. I see, I see, I see, I see. Now I see. Okay, so the morphism G is mapped to a function that, when acting on P, produces P prime.
Yes.
So the morphism G is mapped to a function. The G, which is a function, is mapped to another function.
Yeah.
When acting on P, produces P prime. Which function produces P and produces P prime? G?
The lifted version of G actually.
Okay, now I have another question. Why does the lifted version of G picks P and returns P prime?
Uh, because because well,
That's what a question. Okay.
that's a very deep question. No, but actually, uh, so yeah, this thing here, right, is the lifted version of G, but
Yes.
we define lifting in the context of this home set as precomposition. If you remember, like way back when we were talking about the reader, right?
Mm-hmm.
But precomposition means, well, applying the lifted G to the identity. Well, well, not applying, composing it. It's just G, right? Because you're
Yes.
just composing the identity, so that's a no-op. Uh, but that means that the result is literally just G. But if you remember, when you do the lifting of, when you look at the set, this set here, G actually corresponds to this P prime, right?
Yes.
That means that when you apply this to this, that actually means to compose this with this, which is actually mapped back to this.
You are perfect explanation, Marin. Congrats. I see. And if I am stupid and I see, it's because it was good. I see. I see. Okay.
Well, I'm glad I helped, actually.
Now consider the action FG on Q. Okay, now let's go back. And what the heck is going on? So f of g,
It's this one, right?
yes, yes. And let's apply it on Q. It is some
Yes.
Q prime, a point in f of a. Yes. To complete the
Yep.
neutrality square, P prime must be mapped to Q prime under alpha at A.
Yes, it
P
should.
prime must be mapped to Q prime. Oh, okay, okay. I see the square. I
Yeah.
kind of wished it was like in the drawing, but
There is a drawing here, which is actually
look
yeah,
at this
it's
drawing.
yeah, it's kind of nuts, right?
um.
Look at
Okay.
all those arrows.
Okay. Let's go up a little bit. Let's go up.
Okay,
Let's go back to
let's go
that.
back. Let's go back to that. Okay.
That's true. I can see the square. We picked an arbitrary P prime in arbitrary G and derive its mapping under alpha at A. The function alpha A is thus completely determined.
Yep.
Wait. Wait a moment. Wait a moment. Oh boy, this is very hard. Yes. Yes. So the f of g is actually happening between q and q prime. In q prime.
Yes, it is.
Yeah, that drawing is not helping me. The one above. It's definitely not helping me. Okay. To complete the neutrality square, p prime must be mapped to q prime under alpha of a, which makes
Yep.
sense. We picked an arbitrary p prime and derive
Yep.
its mapping according to alpha at a.
Alpha at A
Ah, I see, I see, I see. I think I see. The second claim is that alpha x, which
is
I already
uniquely
forgot what it
determined.
is.
Uh, it's basically the natural transformation between this thing and this thing, which is like for an arbitrary x, um, you know,
Yeah, is uniquely determined for any object x in C.
that is connected to A,
The
which is
second
this one.
claim is that alpha at x is uniquely determined for any object x in C that is connected to A.
Yeah, because here we were looking at the special case of okay, what if x is equal to A? What if x and A are the same, right?
Yes, yes.
Now we're trying to generalize that to an arbitrary x that is connected to A by a morphism.
Mm. The reasoning is analogous, except that now we have two more sets, this and this, and the morphism G from A to X is mapped under the home functor to
This. No risk of confusion whatsoever.
Okay, I see. So the G is A to X instead of A to A.
Yes, now
I
it's
see.
A to an arbitrary x, which can be anything at all, as long as there's a G starting at A that goes to it.
Wait, so what are we saying? What are the implications of of saying that? We are saying that if oh boy. Ah, what are we saying? We are saying that given an X and given a G and given an A, we are in a home functor and we are in a home functor.
And F has the set category as its target. That's important.
We know for a fact that that this natural transformation exists and it is fully determined. The,
Yes.
okay, okay. So this is I think I'm starting to get it. I'm starting to understand. This is very very strong.
It's very natural.
Very freaking strong. Okay, let's go.
Okay, so again, C from A to G. Again, no risk of confusion, right? Acting on our P, which is the point that corresponds to the identity function. Um, oh, actually, it can be any P, right? We just pick the identity because we know for sure it exists. Is given by the precomposition G after identity array, which corresponds to a point P prime in C from A to X, which is this point here. Naturality determines the value of alpha x acting on P prime to be this thing. And
Since
since P
p
prime
prime. Mm-hmm.
was arbitrary, the entire function alpha x is thus determined. And here's the nice diagram to show it.
Okay, okay. Let's try to read this image a little bit. So what are we doing? We have A, we have G. G is moving A to X. We understand that. There's an identity of A, which is important.
Yep.
And then there's a special case of the home functor, CA dash, that goes to a special home set CAA, in which there is a point P, which is a morphism that lives in there. If I
Yeah.
pick the natural transformation from alpha at A, I go to Q. I go to Q, which is the same category that capital F is gonna give me at some point.
Yes,
Which is,
indeed.
yeah, F of A, capital F of A. Cool. And then there is the CAG, which is the
This,
a home
yes, this,
set. It's a home set of functions.
it's a home set of morphisms, yes, from A to G.
Yeah. No, because G is not a point. G is a function. No risk of confusion.
No risk of confusion. That's already a catchphrase, right?
Okay, okay. Uh, wait a moment. I don't understand the P prime. So we are going from CAA through CAG to P prime.
Which
How?
is the image of this X here.
It's the image. That arrow doesn't have a name. What is that arrow?
That's the C. That's this arrow here. It's the same label. Is just applied as a different. Well, it's actually technically it's yeah, technically it's not really C from A to whatever because the source is not A. It's X. It's C from X to whatever this is.
No, but it's written there. That is CAX. I think that arrow is just there for us to know that the x's are the same.
Okay.
It doesn't have any bridge. Okay, but I want to understand a little bit more. So I don't understand how we go from P to P prime using CAG.
Oh no, I think this is actually the same arrow because see, this is CA blank applied to A, and this is CA blank applied to X, which is CAX.
Ah, okay, so we are filling the blanks.
Yeah.
We're filling the blanks, I see. So CAG is lifting G. I remember we were talking about that.
Yep.
I think you may I'm repeating ourselves here because we already settled this. CAG picks P and gives us P prime. We said this already, but I'm still uncomfortable with it. So
Because there's no risk of confusion at all.
because there's no confusion, but CAG is basically lifting, is because it's a functor. So this is lifting G.
Yes, this is lifting G.
This is lifting G. And if I pick P, which is a function, and I lift that.
Actually, it's a point in a set, but
But
okay.
what that point means in that set? It means that it is a function.
Well, yes,
So P,
it
which
is.
is a function, I'm
Yep,
lifting P, and I'm going to P prime.
right here, yes.
Oh, but P prime is the result of doing the precomposition.
Yes,
I see. Okay, so P prime is there. Then I can, from P prime, go to Q prime using alpha at x,
yep.
and I can go from P to alpha at A,
To
and I can go to
Q.
f of A, and I can lift G using the same f from before.
Yes, you can. And
Uh,
these all
and there is a
commute.
square,
Yes,
which
there's a
means that,
square.
okay, okay, my mind is frying. Okay, I think I understand. I think I freaking understand. So let me read this next part. What if there are objects in C that have no connection to A? So C, the category, and
Yes,
A is a specific fixed thing.
object. Yes,
They are all mapped under CA blank to a single set, the empty set. That makes sense. Recall that the empty set is the initial object of the set category of sets. I also remember that. It
yep,
means that there is a unique function from this set to any other set.
yep.
It means that there is a unique function from this set to any other set.
Which we called absurd, remember?
Absurd peak. What is the type signature?
Absurd goes from void, which is the category with
Empty.
no objects,
Yeah.
it's empty, to anything at all, really. So like there's one absurd for any possible, like starting from the empty set, there's exactly one way to go to any other set, and that's called absurd at a given point.
We have no choice for a component of the natural transformation. It can only be absurd.
Yep.
One way to understand the unit dilemma is to realize that natural transformations between set value functors are just families of functions, and
Yep.
functions are in general lossy. A
Mm-hmm.
function may collapse information, and it may never cover. It may cover only parts of its codomain.
Yep.
The only functions that are not lossy are the ones that are invertible.
The isomorphisms.
Uh, that makes total sense. However, I don't know if I got the first part, which is the natural transformations between set-valued functors are just families of functions, and functions are in general lossy. What does it mean to say families of functions?
Uh, because because of functor, depending on exactly which source category you chose to start with, it will give you a different set. So the natural transformation between two functors is not just a single function from set to set, it's actually a family of functions for all the possible sets that you can start from.
Okay, okay. It's because we can change the A to something else.
Yes, we can.
Uh-huh. It follows then that the best structure preserving set value functors are the representable ones, which again I have to have remember what the representable means because I already forgot. They are either the home functors or the functors that are naturally isomorphic to home functors. Any other functor f is obtained from a home functor through a lossy transformation. Such a transformation may not only lose information, but it may also cover only a small part of the image of the functor f in set.
Yep. Yeah, because it's not an isomorphism, right?
Yes.
Yoneda in Haskell. Finally, we're gonna see some code.
So after all of that,
Yes.
we're gonna have some coding, some code.
Okay.
Okay, so let's go.
So we have already encountered the home functor in Haskell under the guise of the reader functor, which is this, right?
Wait a
Uh,
moment. Wait a moment.
by the way, do you mind if I eat something?
I don't.
Okay. I would ask the viewers in the future, but from their perspective, this already happened, so they actually have no say in this. So,
I don't mind. Okay, but I have another question though. I have another
yes,
question. So the home functor is the one that we go from a pair to a set, to a home set.
yes, basically,
Why is that the reader?
because it goes from this pair to this home set, which is a set of morphisms from A to X.
Oh, okay. So we are calling things pairs and home sets kind of loosely.
Well, what makes a home set is the fact that it's a set of morphisms with the same source and target, right? So
Yeah. No, no, that makes sense. You can eat. I'm gonna continue reading here.
yeah, and the
So the
pair here is just those two, well, input variables, I
yeah, no,
guess.
that's why I said we are calling these things pairs and home sets kind of loosely because there's no notation.
Mm-hmm.
It's only in there, and you're gonna have to like interpret a little bit. So the reader maps morphisms by precomposition. We saw this before. The Oneda lemma tells us that the reader functor can be naturally mapped to any other functor.
Yep.
That doesn't seem to be the case because the Yoneda lemma says that we can map the functor if the functor is set valued.
Well, the reader functor is, in fact, set valued.
No, 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 but we are going from the reader to something else. The something else needs to be set valued, right?
Well, yes, something else also needs to be set valued, indeed.
Okay. A natural transformation is a polymorphic function. So given a functor f, we have a mapping to it from the reader functor.
I mean, I suppose they can take the shortcut because any functor in Haskell, in fact, is set valued by definition because we're operating in, well, they call it Hask because there are buttons, right? But it's really set.
Oh, okay, that's true. That is true. Indeed. So given a functor f, we have a mapping from it, from the reader functor. Yes, so that's the reader functor. We're going to f of x. Okay, as usual, for is optional, but we're gonna use it. The Oneda lemma tells us that the natural transformations are in one-to-one correspondence with the elements of f of a.
This, I
So go.
yeah, I really like the presentation with the code here. But yeah, go ahead.
So we are going from the reader to the f of x, which is a natural transformation.
Yes,
We are saying that this is isomorphic of applying
f of
f
a.
f of
Yes.
a. Man, that's kind of nuts because we are removing x from the equation. Okay,
We kind of are.
the right-hand side of this identity we will normally consider data structure. Oh yeah, so then we go to the whole interpretation of functors as data structures that we've seen before.
Yes.
Uh, the
F of
only
A is
left,
a container of A. Yes.
but the left-hand side is a polymorphic function that takes a function as an argument. The only lemma tells us that the true representations are equivalent. They contain the same information. Give me a polymorphic function of the type that, and I'll
Yep.
produce a container of A. The trick is that we use the lemma. We call this function with ID to get an element of f of A.
Yep. And the converse is also true.
Given a
Given
value of type f of A, one
we can
can
define
define a polymorphic function.
this of the correct type.
Ah, holy balls. Okay, so h is the same h that we've seen before,
Mm-hmm.
which is a to A function.
Yep.
Uh-huh. Wait, h is a to A? Are you sure? No, it needs to be because yeah, it needs to be. Okay, so alpha.
Actually, I think it's actually A to. Well, no, because we're using
Yeah,
identity, right?
yeah, exactly. It needs to be A to A. So we are f mapping that. What is FA? Do you know? Oh, it's f of a.
Mm-hmm.
Ah. Okay, okay, I see, I see. The advantage of multiple representations is that, well, we can have more efficient stuff. Well, we can have stuff tailored to your use case. That's basically it.
Mm-hmm.
And then we have continuation passive style, just for kicks.
Yeah, I was actually slightly surprised when this came up, but this does make total sense because this is indeed the type of a function that takes a continuation and eventually invokes it.
uh, so it's the simplest application of the lemma to the identity functor, replacing f with the identity produces. So
This,
there's no f's because f is the identity functor, which basically does
nothing. It
nothing.
just takes things as they are and passes them through.
So we have a function a to r, and then r. Well, a function that takes a function a to r, and returns an r, and this is equivalent to an a. And why this is continuation passive style again?
And because this function is a continuation, it takes the some input and returns. Well, it performs the entire rest of the computation, which is this. See?
Uh huh. It's kind of crazy. It's kind of crazy. Any type a can be replaced by a function that takes a handler of a.
Yes.
Yeah, indeed, continuation passing style. Okay. A handler is a function accepting a and performing the rest of the computation. Uh, and then R is just the execute well, the output code, like in C would be like -1 or 1 or 0, whatever.
Yes,
This type of programming is very common in some places, which is true.
it is. It's also this is not used as a programming style per se, but it's actually a pretty useful transformation for compilers as well.
Yes, yes, yeah, that's I heard that before. The drawback of CPS is that it involves inversion of control. The code is split between producers and consumers, and it is not easily composable. Anybody who's done any amount of non-trivial web programming is familiar with the nightmare of spaghetti code from interacting stateful handlers.
Hmm.
I don't have a bunch of experience on that, but I imagine. And then we can invert the stuff because we were fixing this source, and now we're gonna fix the destination, and that's gonna go coionida. Of course, it would be.
Of course.
Uh, yeah, I think we can. I don't think there's anything really special here now. And
Mm-hmm.
in Haskell, here's the version of the Coyone dilemma, which is basically the contravariant thingy. Yep,
Confusingly, in some literature, it's the contravariant version that's called the Unit Dilemma. So,
weird. Okay, so do you think we are 53 minutes. Do you think it's possible to like wrap this up with 16 in like 15 to 20 minutes?
um, let's see. Maybe. I mean, after you get through chapter 15, 16 is like more of a continuation rather than anything very groundbreaking, I would say. Uh, I guess we can give it a shot.
Okay, so let's try it.
All right. So we've seen previously that when we fix an object A in the category C, this mapping is a covariant functor from C to set. Yep. Codomain set because the home set is
Is
it's
a
a
set?
set. It's
Yeah.
in the name. We call this mapping a home functor. Yes. We have previously defined sectional morphisms as well. Um,
Well,
that's
actually,
very
let's go a little bit. That's man. I don't know. I think the author is taking too much freedom in the notation, right? Because the notation of the home functor is not x cax. It's a pair ax to cax. It's not the same thing.
mm, well, yeah, yeah.
So that's like no risk of confusion part 2.
Part two, indeed. No risk of what would be a nice tagline to follow this part too, right? Because a sequel needs a tagline, right? Um, well, that's a bit of a tangent. Let's not
Yeah,
go there
yeah.
just now.
Let's vary A in this mapping. We get a new mapping that assigns the home functor to any A.
Which is this.
Wait, now I'm more confused than before. Wait a moment. Have predefined action morphisms as well. Let's vary A in this mapping. We get a new mapping that assigns the home functor CA to any A.
Yeah, basically we're saying instead of fixing the A and varying the output, let's actually vary the A and let's make it a parameter, I guess, would be a different way to put it.
But if you
Yeah,
do
this
that,
yeah, this is not quite the same as this, right? You see,
yeah, it's
here
very, very different.
yeah, we're mapping A to an arbitrary functor that starts at A.
Okay, that's a better way to say it.
Yeah, now it's a mapping of objects from category C, because A is in
A, it's from
C, to
C.
functors, which are objects in the functor category.
So this is an network transformation.
Uh, well, I guess. Is it?
But yeah, because we are going from the category C to the category of functors.
Well, but it's not a mapping between functors, is it? Well, it
Oh,
actually is. Huh. It
no,
actually
no,
is.
actually, that's not true because wait, we need to know if C is a functor.
No, C is a category, A is an object in C, but then this thing here is a functor. It exists in the functor category, so it is in fact. Uh, well, no, I
It's
think
a
this is actually
functor.
a functor. This
Yeah,
is a
it's a
functor.
functor. Yeah, but it's kind of mind bending because you're going from C, which is a normal category, to another category, but it just so happens that the other category is the category of functors. So
Yes.
it's a functor. Okay. Ah. Okay, so let's use the notation C set for the functor category C to set.
Okay.
You
You
may
may
also
also
recall.
recall that home functors are the prototypical representable functors. Yeah, because they are indeed. There is a set that corresponds to them, so there is a representation of them in the set category, essentially.
Okay.
Every time we have a mapping of objects between two categories, it's natural to ask if such a mapping is also a functor. In other words, whether we can lift a morphism from one category to a morphism in the other. A morphism in C is just an element of C from A to B, but a morphism in the functor category from C to set is a natural transformation.
Wait a
There you
moment.
go.
Why a morphism in C is an element of a home set?
Because that's true by definition. A home
Oh no
set.
no no no! I'm stupid. That's a stupid question. Of course it is. It needs to be.
Mhm.
uh, okay, no, I got confused because I thought the morphism is the home set. No 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 no. It's an element of the home set. But a morphism in the functor category is a natural transformation. Makes total sense.
So we are looking for a mapping of morphisms to natural transformations.
Nuts. But okay.
Kinda crazy. Let's see if we can find a natural transformation corresponding to the morphism f from A to B. First, let's see what A and B are mapped to. They are mapped to two functors, these two,
Yep.
and we need a natural transformation between the two. And here's the trick: we use the dilemma.
Okay. Wait a moment. So what is written in there? So that notation C set means that this is a functor.
Yeah, it's a functor category from C to set.
Uh,
Well, it's a functor category where the functors inside of it have C as the source and set as the destination, as the target.
okay, so this is a set of functors.
No, it's a category of functors,
It's
in
a
fact.
category of functors. What are we doing? We're
Yeah, this is
grabbing.
just the. Yeah, this is just the Yone dilemma, and we're replacing f with this home functor, which is what we're trying to do, right? And we
Uh,
get this thing.
my mind, wait a moment. We need a natural transformation between two functors.
Yep.
Ugh. Wait. Uh, so we have f, which is a to b. That makes sense. Let's see what the a and b are mapped to. So when you lift them, you go to that. That makes sense. We need a natural transformation between the two functors. Which two?
These actually,
These two. And
these
then
functors.
what are we doing? We are grabbing the unit lemma, which is that, and we are replacing f. Ah, okay. So the unit lemma is working as a recipe to find the natural transformation between the two functors.
Mm-hmm.
Uh-huh. Okay. Okay. I see. We can continue. We can continue.
So this is exactly the natural transformation between the two home functors we were looking for, but with a little twist. We have a mapping between a natural transformation and a morphism, an element of C from B to A, that goes in the wrong direction, right? Because it's from B to A, but
Yeah,
we
but
were
every time that
looking
happens, that's easy now because we just contravariant time.
contravariants indeed.
Okay, wait a moment. Scroll up. I
Okay,
want to understand this as best as I can. So scroll up a little bit more. So
okay.
in the Oneda lemma, the left side of the equation, it was not written like that. It was written net, right? Of natural.
Yes, but a natural transformation is just a morphism in the category of functors, which is, well, this is a functor category, so
A natural transformation is a morphism in the functor category. So this is exactly the same thing. Okay, so let's go over the drawing for a moment there. So
okay.
the drawing is saying that we have an A, we have an X, and we have a B. We have various ways from going to A to X, and various ways from going to B to X.
Yep.
If we apply the functor in which fixes the A, we go to C.
AX.
Uh, I am. That's. Is that a category? What is CAAX? Is that an element?
It's a home set, actually.
It's a home set. That makes sense. That makes sense because X can be anything. So the blank is basically. Yeah, I would prefer blank in there, but okay.
No, the
Uh,
blank here is because this is a functor, and this is the home set, which is the image of that functor in set.
yeah, no, but I'm having initially I have a hard time saying how the X went from the left to the right. It didn't. It's just because the X has the semantics anything.
Yeah, X is whatever, as long as it can be the target of those two things here.
Yes, yes. So we have that. We apply the same treatment to B. That makes sense. And what we are looking for? What is the CBA?
This is the isomorphism that, well, the other side of the isomorphism that we're looking for, right? Because we're
Uh-huh.
looking for this natural transformation, and it is isomorphic to this by the Yoneda lemma, substituting this with F.
Okay. Okay, now we can go to the drawing with the contravariant.
Okay, one moment.
Sure. Uh,
Um, right, so yeah, this goes in the wrong direction, but that's okay because that means it's just contravariant. Amazing.
yeah, so we have an A and a B, and we have a function. We have functions going from B to A. Makes
Yep.
sense. And we want to understand. Uh, so the CA blank and the CB blank are the functors. The
Mm-hmm.
arrows are the natural transformations.
Mm-hmm.
Aha, okay, I understand this. I understand. The mapping from C to C set is not only a contravariant functor, it is a fully faithful functor. Which I remember this. I remember when I was reading. This is a very interesting nomenclature for it. So,
Yep.
Fullness and faithfulness are properties of functors that describe how they map home sets.
Indeed.
Fullness and faithfulness.
And here are the definitions.
A faithful functor is injective on home sets, meaning that it maps distinct morphisms to distinct morphisms, so it's not collapsing anything.
Yes.
Uh, okay. A full functor is surjective on home sets, meaning that it maps one home set onto the other home set, fully covering the latter.
Yes, that
So,
means
so the codomain is covered.
yes, there's no possible thing in the codomain that is not a possible output of this full functor.
Yeah, it's intuitive. It's full. Cool.
Yes, it's full. It's very full. And a
So,
fully faithful functor is a bijection. That is, it's full and faithful at the same time.
so you're not collapsing and you are covering the entire codomain.
Yes,
For every
that means
pair of objects A and B in the source category C, there is a bijection between CAB and DFAFB. So what is D in there? F is the functor, I believe.
this is the target category of F. Well, in our case, it's this, right?
Yes. This doesn't mean that F is a bijection on objects. There may be objects in D that are not in the image of F, but we can't say anything about home sets for those objects. Wait a moment. There may be objects in D, which is a target category of F,
Yes,
that are not in the image of F. How is that possible?
because this is not a bijection. This is not a bijection of, well,
Oh, the objects that we are talking about are morphisms.
yeah,
Jesus. Okay, that means that it doesn't matter the objects at all. They may be collapsing in everything.
but
However,
then,
the morphisms
yeah,
they need to be maintained.
yes, they need to be one to one.
That's very weird. That's
It's
very
very,
weird.
it's very unusual. Yes,
That's very weird. Okay, let's continue. So what's next there? So the contravariant
the
functor we have just
embedding
described, the functor that maps objects in C to functors in...
C2 sets.
Yeah, we've
Well,
seen this before. Defines the Oneda embedding. It embeds a category C,
which is this thing.
well, and then theoretically speaking the COP because it's contravariant, whatever, blah blah blah, minor details. Inside the functor category C
Yeah,
set.
yeah. Let's just invert the directions of every single arrow. Minor detail.
It not only maps objects in C to functors, but also faithfully
Faithfully.
preserves our connections between them.
Yep.
Wait a moment. Let's see if I understand this statement. So it embeds a category C inside the functor category. What does embeds means in this case?
Uh, that means that there is, if you restrict yourself to a particular, well, subcategory, I guess. I was going to say subset, but these are categories, not sets. But basically, a fragment of this thing is isomorphic to this thing.
Ah, okay, no, that actually makes sense because you're going from A to CA blank. So I guess, yeah, okay. So
This was,
it is in a sense the same kind of semantics of a subset.
yeah, kinda.
Okay, okay, semantically. Cool. So now, this is a very useful result because mathematicians know a lot about the category of functors, especially functors whose codomain is set.
This
We
was news to me when I read it, but okay.
we can get a lot of insight about C by embedding the functor category. Okay, okay, okay. So here's the hack then. You don't know a lot about C. However, you know a lot about functors. So if you embed one into the other, you can have conclusions about C because you can embed it in the other one.
Yes, exactly.
Ah. Okay, tricky. Very tricky thing.
And of course, there's a dual version, because of course there is.
Of course there is. Uh,
Naturally, there is.
yeah, this is not worth reading it word by word. Let's just move on.
I just want to note that contravariant functors from C to sets
Yeah.
are familiar three sheaves, which is we saw like a while back.
Yeah, which I already have very little recollection of it.
So application to Haskell, and here's the code finally.
Okay, so the another
Uh,
embedding can be represented as the isomorphisms between natural transformations,
Amongst
between
reader
readers
functors
on
on
one
one
hand, and
hand,
functions.
functions
Ooh,
going in the opposite direction specifically.
that's that's crazy. Okay, remember the reader function is equivalent to that. I know that.
Yes,
The left-hand side of this identity is a polymorphic function that, given a function from a to x and a value of
of
type
type B.
b, uh, can produce
Yeah,
a value of type x.
yeah, this is basically this except uncurried, right?
Oh, okay, so he's uncurrying it. I remember that. The only way this can be done for all x is if our function knows how to convert a
A B
b
to an A.
to an
It
a.
has to secretly have a B to A function inside of it.
Wait a moment. Wait a moment. We'll scroll up a little bit. So we
Okay.
have a function from a to x. We have a function from b to x. We are saying this is isomorphic from having a function b to a.
Yes.
Uh, how are we doing that, bud?
We're going to use the Yoneda trick of, okay, what if we give this thing here, this overall arrow, the identity function as the input? Yeah, it's literally just this.
No, no, no. I remember the trick of using identity. So then you can coerce x to be an a, and then well, everything is rosy. Uh, but that seems to be the only solution. You
Yeah,
need to do
because,
this.
yeah, here's the intuition. For all x, if you have this type, right, for
Yeah.
all x, that means that,
Yeah, there's no
okay,
way around it. A x needs to be a.
yeah, no, x, no, I'm not talking about fixing x. Okay, if you have a function that indeed for all x has this signature and it exists, is valid, type checks, everything, that works.
Sure.
For it to take a function that expects an A and turn it into another function that expects a B, for that to even be possible, it needs to be able to turn a B into an A.
He needs to be able to pick a b and turn that to an a. Wait, repeat what you said.
Yeah, because for it takes an argument which expects an A,
Yep.
it turns it into something that expects a B.
Yep.
For that to be possible, the thing in the middle that does this conversion needs to be able to say, okay, if you give me a B, I can figure out how to get an A to give to this thing. You see?
I see, but do you agree that let's suppose that you have that you have an ability to pick a B and get an A and pass the A to the first there. You're not gonna have an A, you're gonna have an X.
No, but the X is like, okay, this function takes an A and returns an X, right?
Yeah.
I'm gonna tail call it so I can return the X that the first function returns.
But that's
See,
not
this
what we
X,
want. We don't want the X. That's what I'm confused about. We want an A.
no, the final result is an X. See, it's the very last thing in this
Ah,
arrow
okay,
thing.
okay, okay. I got confused. I confused identity with isomorphism. So, indeed, the output of this will be an X, but this is isomorphic from doing the function B to A.
Yeah, this thing is isomorphic to this because one implies the other. If you can take a continuation returning an X and expecting an A into another continuation expecting a B and returning an X, returning an X and expecting a B, you need to be able to do this step somehow. Like, you can't go from this to this without this.
That makes total sense. And that's the trick. That's the kick. It has to secretly have access to a function. So and then we have the Haskell implementation, which makes total sense. So you have an XA, uncurry that. So then you're gonna have receive a B separately. You
Yep.
have access to a secret function called B to A.
Yep.
You pass the B to it, you get the A, and then you pass that to F. It's gonna return an X, and that's exactly how that type checks.
Yep.
Given a function from Y, we can recover the converter by calling from Y with the identity.
Yep.
Given a function from Y, we can recover the converter.
Yeah, because in this case,
Yeah, I
F
see, I
would be
see, I see.
identity, so we are just left with this.
So why is this establishing a bijection though?
Because basically this implies this, and the other way around. Like,
The other way around. Uh, I can see the first way. From Y implies B to A. I can see that. But why does B to A implies from Y?
because you're just composing it to a function argument.
Hmm. Not. I'm not. I don't see it. See it.
Like, this is just a pre-composition, right? If you have B to A, you can put it in front of an F to convert its arguments to an A, from a B to an A. So you
Oh
can
yeah.
now take a B.
Yeah. No. In that case, yes. I understand that. Okay. So an alternative way of looking at this isomorphism is that a CPS encoding of a function from B to A.
Yes.
The argument x a to x is a continuation. The
Yep.
result is a function from B to x, which, when called with the value of type B, will execute a continuation precomposed with the function being encoded.
Yes, which is basically this.
Yes. The embedding also explains some of the alternative representations of data structures in Haskell. And then, yeah, I heard this before. The people use this type of shiz in lens.
Yep.
So then, how much do you have left? We are almost in 1 hour and 20 minutes. So how
And
much?
this is the last part of this chapter. Well, no, it's not. There's naturality as well. Yeah, this
Okay,
is
so
just like 3 pages.
okay, let's try to do this in 13 minutes. So priority example. Oh yeah, this was the thing that I mentioned to Mageta. So this
Robert Harper, yes.
yeah, Harper is being there's a Harper in this book.
Yes.
A preorder is a set with an ordering relation. Yeah, this is a classic thing, right? So a preorder is a set with an ordering relation between its elements that is traditionally written as that.
Yes.
The relation needs to be transitive, being reflexive, but not necessarily anti-symmetric.
Yeah, it's possible to have cycles, so it's not actually a proper ordering. It's a pre-order. See?
I don't remember. Transitive means that if A is less than B and B is less than C, A is less than C, right?
Yeah,
And the
like,
reflexive means that if A less than B and B less than A is equal to B.
yes.
And I don't remember what the heck is anti-symmetric.
Antisymmetric means that if A is less than or equal to B, and it's not actually equal to B, it cannot possibly be the case that B is less than or equal to A. Basically saying no cycles.
Maybe I'm too tired to understand that. But we can proceed. I remember pre-order. It's fine. We already seen the pre-order forms a category. I remember that.
Objects are the elements. Morphisms are, well, either they don't exist if they cannot be compared,
Mm-hmm.
or if it's not true that they are in the correct order,
Mm-hmm.
or they exist if A is less than or equal to B and it points from A to B.
There is never more than one morphism from one object to another. Makes sense. Therefore, any Hom set in such a category is either an empty set or one element set. Makes sense. Which is, and then we have it's called thin, which is
Mm-hmm.
funny, but okay. Instead of singleton, they call it thin. It's easy to convince yourself that this construction is indeed a category. We've seen this before.
Mm-hmm.
It is associative. They have identity because an element is equal to itself. Blah 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 blue. Let's go on.
Koyoneda, yay.
Coordinated time. So we are interested in the action of morphisms. So we have this. The home set on the right hand side is non-empty if and only if A is less equal to B, in which case,
Mm-hmm.
as we've seen before, it's a one element set.
Mm-hmm.
And then consequently, there exists a single natural transformation on the left. Otherwise, there is no natural transformation. What is it? What is a natural transformation? It should be a family of functions between sets. Uh, each of these sets can either be empty or
Or a
singleton.
singleton.
Let's see
Yep.
what kind of functions are there at our disposal. So why is that the case? Why is the family of functions between these two sets?
Uh, we're interested in its actions on morphisms, right? Well, this is a Koyoneda embedding, right?
Oh, that explains why the A and the B are on the right.
Yes. And we're applying to the pre-order category. Well, actually, yeah, this explains this, right? So,
No, I think I see. I think I see. Let's continue.
yeah,
There
and
is
the
a.
reason they can be either empty or a singleton is because, well,
That's
we
how
just saw
pre-order
it.
works. Yeah, that's how
It's how
pre-order works.
pre-order works, yeah,
Yeah, pretty much. Okay, there is a function from an empty set to itself.
which
The
is the identity.
identity acting on an empty set. A function absurd from an empty set to a singleton set. It does nothing since it only needs to be defined for elements of an empty set of which there are none. And a
Of course.
function, for, yeah, but that makes sense. And a function from a singleton to itself. The identity acting on one element set. The only combination, okay, so as far as I can tell, we are exploiting properties of the preorder to to tailor down the Koyoneda lemma and the
Yes,
Koyoneda embedding.
yes.
I see. The only
The
combination
only,
that is forbidden is the mapping from a singleton to an empty set. What would the value of such a function be when acting on the single element?
yeah, yeah. That's a troublesome spot, right?
Wait, I don't know if I follow that. So the only combination that is forbidden is the mapping from a singleton to an empty set. Why?
Yeah. How do you turn something into nothing?
You just ignore.
Do you?
Oh no, but then you need to have, yeah, that doesn't make sense because then you need to have an element from the empty set, and you cannot do that.
Yeah.
I was kind of thinking void, right? The function void, which takes anything and returns unit. Actually, no, that's the
Mm-hmm.
function unit, not void.
Mm-hmm.
Okay, so a natural transformation will never connect a singleton home set to an empty home set. In other words, if x is less than or equal to, than a, single home set, blah blah blah. A non-empty xb means that x is less or equal to b. Oh, okay, so they close the parentheses and I didn't see that.
Yeah.
Then cxb cannot be empty. A non-empty cxb means that x is less or equal to b. That makes sense. So the existence of the natural transformation in the question requires that for every x, if x less than a, then x less than b. Wait a
Yeah.
moment. How can we say that?
Because for this to exist, um, this thing cannot be empty. Like,
For this thing to exist. Ah, I see.
because of this, right? Since you can't go from a singleton set to an
If
empty
you go to
set,
a singleton, there must be a singleton in the other side.
yeah,
Aha. Okay, so for all x, x less than a implies x less than b. Cool. On the other hand, Koyoneda tells us that existence of this natural transformation is equivalent to CAB being non-empty.
yeah, which is the other side of this thing, right?
Yes, it's the other side. So go down. Together we get A less than or equal to B if and only if for all x. Crazy. we full circle. We go to the beginning. You
Yeah, we could have arrived at these results directly, uh, but it's pretty interesting and exciting, apparently, that we got to it through the Yoneda embedding. It's like,
No, it is kind of what I said 2 sessions ago. We were using category theory as a way to understand things and then go back to the domain that we are interested in. It's kind of the same analogy that I always use about time and frequency in electrical signals. So
yeah.
you want to be on the domain of time because that's what humans care. However, if you go to the frequency domain of the signal, you can talk a lot more shiz about it,
Mm-hmm.
and then you go back and forth between the two. So that's basically what we did with the Yoneda embedding. We established the recipe. We are using the Yoneda lemma as a recipe. We are getting conclusions out of that. Then we go back to the domain that we care, and then we have a statement. But in this case, it was a trivial statement.
I mean, kinda. Kinda trivial, kinda not. It is interesting that, like, okay, we just need to establish the connections between the morphisms, and then Yoneda gives us the ordering relation that's usually taken as the definition of a pre-order, right?
Yeah, no, that's why I said trivial because that's the definition. That's the thing. We went full circle, but that was a demonstration of the power of the tool.
Yeah, very nice, very interesting.
So now naturality.
Yeah, the Yoneda lemma establishes the isomorphism between the sets of natural transformations and an object in set. Yes, natural transformations are morphisms in the functor category from C to set. Okay, and the set of natural transformations, there's an S missing, between any two functors is a home set in that category.
Wait a
Also
moment.
true.
The set of natural transformations between any two functions is a home set. Yeah, that makes sense.
And the Yoneda lemma is this isomorphism, which we just saw.
Boom.
Uh, Turns out to be natural in both F and A. In other words, it's natural in this pair,
A
which is
pair
taken from
taken
the.
from the product category.
Yeah.
Wait a moment. So we are making a product between the category C and the category of functors.
Yes.
Uh-huh. Okay, no, that makes sense. Notice that we are now
Notice
treating F as an object.
in the functor category. Yes.
Yeah, I see what you're doing. Let's think for a moment what this means. A natural transformation is an invertible natural
Natural
transformation.
isomorphism is an
And a natural
invertible. Yeah.
isomorphism.
And indeed, the right-hand side of our isomorphism is a functor.
The
Um,
right hand side
this.
is a functor.
From this pair to set,
Yes. Yes.
it's an action on a pair F and A. And its action on a pair F and A is a set, the result of evaluating the functor F at the object A. This is called the evaluation
Wait.
functor.
Ah, we are 2 pages to the end. I need to get this. Wait a moment. It's a natural isomorphism is okay, and indeed, the right hand side of our isomorphism is a functor. F of A, right? That's what it's saying.
Yes.
It's a functor from the Cartesian product of functors and C to
Yep.
set. Uh, it's the Cartesian product. I'm not seeing the Cartesian product.
It's this.
Yeah, but that's not on the left hand side. Wait a moment. Oh, it's only about the right hand side. What we're saying right now, it's only about the right hand side.
Yeah,
So it's everything about the F of A.
we're going from right to left here.
Yeah, very Haskell-like. That's okay. So it's a functor from that to that. It's a functor from that to that. It's a pair. Its action on a pair F of A is a set. The result of evaluating the functor F at the object A.
Which is F of A.
This is called evaluation function. Oh, wait, I'm not getting this part though. Its action, it is an action on a pair. Its action on a pair is a set.
Yes,
Ah,
because f is a functor that goes to the set category.
I remember that. Oh, that explains it. Thank you, Marinho. So I forgot about that. F is a set valued functor. Ah,
Yes,
cool. The left-hand side is also a functor that takes this to a set of natural transformations.
this, which is, this.
The left-hand side is a functor that takes this. Okay, I guess.
And to show that these are really functors, we should also define their actional morphisms.
What's a
But what
morphism between a pair and this? It's a pair of morphisms, of course. The first being a morphism between functors, hence a natural transformation, and the second being a regular function. The evaluation,
morphism is, yeah,
the evaluation functor takes this pair and it maps to a function between two sets.
these two.
Takes this pair and maps it to a function between two sets.
Yes.
My mind is fried. Wait. Why is this mapping from the two sets? Between these two sets?
Because this thing goes from F to G,
Which is a
right?
natural transformation.
This thing goes from A to B,
Okay.
and you can lift F using either of the functors depending on whether you already went through the natural transformation or not. Like this or this.
The square.
The square, yes.
Uh-huh. Uh-huh. We can easily construct such a function from the component of the natural transformation at A, and the morphism F lifted by G. Notice that because of the naturality, hence the square, this is the same as this. Ah,
I'm not going to prove the naturality. The proof is pretty mechanical. It follows from the fact that our isomorphism is built up from functors and natural transformations. There's simply no way for it to go wrong.
yeah, that's another catchphrase. No risk of confusion, and there is simply no way of going wrong.
Yeah, it's very natural.
Okay, can you? Okay, so I just want to
Now,
know. Let's scroll up a little bit.
okay.
I still want to understand what this means. The evaluation function takes this pair and it maps to function between sets. You scroll up a little bit too much.
Too much, okay.
Yeah, it maps to a function between these two things.
Uh, evaluator function.
Ah,
Which,
it's
where
down.
exactly is it?
It's down there. The evaluation function takes this
Okay.
pair and maps it to a function between two sets. Uh,
Oh, right. Yeah, because, well, you have this pair, which is the input, right? Right?
yes,
And you have the natural transformation between this F in the input and the G, which is in the output, right?
yes,
And likewise, you have the function from A to B, right?
yes. No, I understand the pair that we have. The pair of
Okay.
having the natural transformation and the f, that's okay. I just don't understand how we are mapping. How is this mapping, the functor mapping that to a function between two sets? That's what I'm not following.
It's because f of a, f is a set-valued functor, g is also a set-valued functor. You are applying those, so the results of this is a set, and this is also a set.
Ooh. Ah. Okay. Okay. Jeez. Okay. I see. So the real trick is that we have a natural transformation to go from one function to the other,
Yep,
and we have a function f that picks the elements and go from one to the other.
yep,
But we know ahead of time that the functors both go to sets.
yes,
So if you apply the individual elements to each of functor, you know you're gonna go to two separate sets.
Yes.
Uh-huh. Okay. I think I have well, at least an initial understanding. Okay, this was very freaking hard. Anything else? I'm gonna finish the recording.
No, bye, future people.
Bye.